quite new today, folks. We're going to introduce the final big element of the AnyLogic modeling vocabulary as far as building up agent-based models in AnyLogic. And that is going to be introducing mobility, okay? We're going to go introduce mobility into our models. And we're going to do it in a set of stages. First, I'm going to talk with you a little bit about the spatial environment and the types of spatial environment afforded to us within AnyLogic and the types of contexts where they might be helpful. We're then going to go in and talk about the mechanisms needed for a little stylized example, and then we're going to put in place some more grounded example, an example that is a little bit more texture to it and relevance to health, which involves hybrid modeling. Your first taste of hybrid modeling, where we're going to have people in a population presenting for care in clinics and healthcare facilities. Okay? Okay. So, ladies and gentlemen, the first thing I want to talk about is the embedding of people in space. In order to motivate this, I'd like you to go to main, and I'd like you to go down to the place that we were just at a few minutes ago, which was highlighting the layout for people. Okay. So if we go over here and we open up any one of these models we've built, say this one from earlier, and we go to main, and we were to scroll down, you notice that in this environment for other agents, it gives choices of a space type. We can actually choose in what sort of spatial environment do we wish our agents to be embedded, to be situated. Is it a continuous environment, a situation where we have space as finely divided up as needed, sort of like we have time as finely divided up as needed, where agents can circulate, they can be at location, X location 20.5, Y location 32.17, and another agent can be immediately nearby. Here in a continuous situation, we typically view it as a situation where essentially agents are quite small relative to the environment. We don't have to worry about agents being mutually exclusive in terms of their location, that they exclude each other. Instead, they're viewed as being able to pack in reasonably closely. It's kind of like viewing the landscape from a plane. You see the cars and so on, but you're not concerned about all the details of being able to recognize cases where one car needs to go around another. They're really, really small compared to the landscape. As far as it looks to you, they can kind of pass each other very closely. You don't really see them as excluding each other. By contrast, a discrete environment, we have the space divided up into squares, into grid cells. And in a given grid cell, you can either have 0 or 1 agents. So you might have a house or a store or a brownfield, an area that's unoccupied. You might have a farm there or a residential use if it's occupied. So here with a discrete space, it's broken up into this grid, and you can either have 0 or 1 agent there, but not more than that. It's mutually exclusive. Okay. Finally, there's a GIS space, which is currently is able to capture things like the latitude and longitude associated with agents, their bearings, so their heading, when they're moving in a certain direction, what's the appropriate heading in terms of compass degrees. Within the next version of AnyLogic, which they're anticipating release in October, this is going to be much, much larger and much, much richer in terms of its implications. Being able to query proximity to certain types of resources or find the shortest route on city streets from one place to another or on bike routes. Right now, however, we can tag agents with latitude and longitude information and track them around the space and use that, and also load in shape files which define the basic features of the space and use that to further as a framework for loading in things like terrain type or use of buildings, etc. So GIS capabilities are notable there right now, but are going to be much richer in the near future, and it's a space worth watching. Many of our collaborators in the health space are very interested in the GIS side of things, and I think there's a lot of reasons to be quite excited about that. So let's talk just a few minutes about these things. So agent spatial embedding is key for expressing dynamics for certain types of problems. Often we have locality of influence. We have local transmission of norms, attitudes, beliefs, ideas, and pathogens. Sometimes spatial embedding gives insight into certain phenomena, spatial concentration, say, of pollutants, percolation of certain influence or certain substances through the environment, travel from one place to another. And spatial reference modes, cases where we have spatial patterns we see in empirical data. For example, in rabies data, we often will see waves of infection spreading out. And if we wish to understand those, embedding people in space makes a lot of sense, embedding our agents in space. And finally, can support GIS integration, which, as I mentioned, for a lot of needs is of keen interest. So you can ask, how close is this person to a fast food restaurant or to billboards promoting tobacco? How close is this person to a park or to a grocery store versus a convenience store? So by embedding people in space, we can capture a lot of these features. And I talked about these three basic types of environments that are supported by AnyLogic. This last type we'll be examining in less detail, but it was a rich part of the presentation yesterday that Sarah gave. Sarah talked about having these different types of agents moving around, and she had storefronts, and people could move to the storefronts. Those were located in a discrete grid of cells where you'd have either a store or a home or an empty space there. So they're divided into columns and rows. If anyone here is familiar with NetLogo, it has this notion of a patch, a set of patches, and this provides a somewhat similar environment. Yeah. Yeah. So you mean, could they be associated with like a geofence or something like a? That's a good question. I couldn't answer that off the top of my head, but I'd be glad to ask a TA to partner with you this afternoon to dive down and let's find out if it's the case. Yes.
In version 6, at least, we were able to represent census blocks as agents.
Great.
And those have various shapes. So.
Terrific. There you go. So yeah, Sarah can comment. Version 7 is only right now. I think it's probably at par with version 6 features there. 7.1 is going to be a totally different world in terms of GIS integration, and there's a lot planned for that, and a lot already implemented for that. So, but I think if you could do it for version 6, then yes, you should be able to. But again, like for any of these questions, if you can't get a good answer from me, grab one of the TAs and let's drill down and let's get an answer. Okay? Okay. Thank you, sir. That's very, very helpful. Okay. So within AnyLogic 6, as some of you may know, there's this explicit environment. Here, what we have in AnyLogic 7, it's really in main. It's that little area of main we were just looking at in the properties of main. There's no separate environment now. Each agent automatically provides an environment to agents embedded within it, and that includes main. So, for example, this area here is where we specify the features of the situation. Continuous, discrete, where we have columns and rows, or GIS, okay? So GIS, we can load in GIS map, and we've had some luck loading in GIS shape files, although we did have some issues that weren't immediately obvious about why a GIS file didn't work at first, but which could be resolved through consultation with the folks at AnyLogic. So in any case, we could situate people in space, and I want to talk a little bit about these types of space. In order to help you understand these, one thing you might do is to load in a model that I've provided you that provides an implementation of what's known as the Schelling segregation model. And it's actually known as continuous time Schelling segregation here. It's this model here in the set of example models. And if you load this in, this illustrates a situation where we have a discrete space. So we have people arranged into a grid in space. And I'll show you the sort of behavior we'll get out of this. So here we have this underlying space. Things are divided up into these little grid squares, and a given grid square is occupied by people of one or another, of one or zero groups. So according to their color, they're from the green group, the black group, or the red group, and they're competing for jockeying for position in different areas of the space. Now, here we have space divided up into these rows and columns, and the way in which that's accomplished is that here, within main, we have people specified as being in a discrete space with a certain number of rows and a certain number of columns, and there's a neighborhood imposed upon them. This neighborhood defines how many neighbors they have, whether it's the neighbors in the 4 cardinal directions or whether it's all 8 neighbors. And occasionally I get these confused, but I think more is 8 neighbors, and Euclidean is just the 4 neighbors, north, south, east, and west. So here we have people arranged randomly within the space, but in either a more Euclidean neighborhood. And what that means is each person has a certain number of neighbors around them with whom they can interact. In this particular model, the situation is such that a given person here is located in a certain place, and periodically they could consider a move. If they're currently satisfied, as called by this function called isSatisfied, they stay in place. If they're dissatisfied, they jump to another space within the broader location where they hope their preferences will be better met. So they jump to an empty cell within the space. This is an AnyLogic built-in function. It has this notion of an empty space. And they'll try again. And while I don't have time to go into this in too much detail, this isSatisfied function here takes into account their tolerance level for living beside people who are from a different group. Okay, so we consider their neighbors. We count the number of neighbors who are of a different group versus their own group, and if the fraction of the neighbors that are of a different group exceeds a certain threshold with which they're comfortable, they will move. This model was first introduced in a somewhat different form by Thomas Schelling in I believe it was the 1970s, to examine the emergence of residential segregation within cities. And the general realization here is that with fairly modest preferences as to people's for modest preferences as to whom they live next to, you can get emergence of some pretty interesting longer-term patterns. And I thought this was actually exhibiting those patterns over time based on the settings that I have here, but it may take more time than we have. So here we have agents. They move to different neighborhoods, and they do so until they're in a position where they're satisfied, and their satisfaction will change over time if there's other agents moving in to nearby them. I'm going to load a different version of this model, which might exhibit more interesting behavior here. just so I can exhibit it more more closely. So here we have a situation where, for example, you see an emergence of patterns at a macro level that reflect grouping of people of similar ethnicity. So this is the other model called continuous time selling segregation with free cell list. So I loaded this in, and that's indeed the one we want. I apologize for pointing you to the other. It's this one right with the name that's very similar, but has free cell list at the end. And this is a model I built in LA to when I was talking with someone who's from the Department of Sociology about these phenomena. So here you see people assort into neighborhoods with people who are similar to them because they have only a certain tolerance for living in neighborhoods with other people. And even with slight preferences, you can get significant patches emerging where people are clustering with nearby people. So slight preferences can lead to quite striking visual patterns. The big point I want to convey to you is each of these little dots corresponds to a patch of land that's occupied by either zero agent, shown by white, or a single agent, shown by associated with a different color. And people move around. Here they're moving to the empty cells. Okay? So this is an example of discrete space. We're going to see a hybrid model that exhibits discrete space a little later today. But this is a quick glimpse of discrete space. What's also notable is that many discrete space models, not all, but many, also use discrete time, where time moves not in a continuous fashion, but in lockstep. Everyone updates at the same conceptual time. And the AnyLogic version of this model, the original AnyLogic example model for shelling segregation, exhibits this discrete time components, which is classic within traditional agent-based modeling. Discrete time situations where everyone is going in time steps, they all update at the same time, has a certain clarity to it, but it tends to be quite complicated because of the need to broker competing events. So if you have the same person and there's multiple processes that can infect that person, trying to figure out which of those processes has happened first within the past year to figure out how to record the various events can be a significant chore. For example, if someone's simultaneously at risk of dying versus developing end-stage renal disease, and you want to record a count of incident cases of end-stage renal disease over time, and you're updating people every year at the same time, you have to figure out now, okay, which of those events took place? Maybe this given person has both died in the past year and has developed end-stage renal disease, supposedly in the past year. Which of them occurred first? Because you don't want to record them as having, as part of the statistics, as having recording end-stage renal disease if they would have died first. And that becomes a pain. Also, if you have multiple agents who update at exactly the same time and want to move to the same space, it becomes difficult. They clash. So AnyLogic supports continuous time to simplify this reasoning. Things happen at their natural times. But be aware that a number of models within AnyLogic use what are called time steps. And you should be aware that it is a popular type of approach in agent-based modeling, but it's fraught with certain types of complications. Any questions on that? Do people want me to expand on that? I could show you a model with discrete time steps if people want to see it. Dylan.
Or does anyone have a roughly even completion of a particular model
it doesn't, in AnyLogic, it doesn't impact it in a very significant way. You are correct at a level of the underlying computational plumbing. You're correct, and I must say, as your supervisor, you're perceptive. to pick up this fact that discretization of time can lead to opportunities for parallelism. Fundamentally, you're going to be able to go off and handle these different agents who need to be updated potentially at the same time concurrently on different processing units, such as in a GPU, a graphics processing context. And we are working in a separate project, the FRABGIS project, with Chris Duchin, doing things like that. But none of the platforms that I'm aware of for agent-based modeling take advantage of that now. It's just ours that is one that's looking into that opportunity. But you got to balance between that. I'll be with you in just a second. You got to balance between that and the fact that at a conceptual level, it's easier to describe typically in continuous time. Yeah. Question?
Much less sophisticated question. When you use this model to have conversations with stakeholders,
right.
Some of the versions, some of the ways that people have used this in the past use displays where stakeholders could actually move sliders and say, okay, well, what's the preferences?
Yep. Exactly.
Are you going to talk at all about how we take our models and
absolutely
move them into an environment
where
the visual representations are a little easier for people?
I would be happy to do that, George, and I'm grateful for you raising that. It's one of those things that I'm not sure when to weave into the week, and I was pushing it to later. We can add that to our model this afternoon. Yeah, this afternoon. It is, ladies and gentlemen, the good news is here, when it comes to AnyLogic, and you can go take a look at it here in your model. If you have a model open, if you scroll down in this palette, about the fifth one down here, it's called Controls. And here we can drag into our model buttons, checkboxes, edit boxes, radio buttons, sliders, as well as a bunch of other features. And these allow us to build up a model with rich user interfaces and actually build up the basics of the user interface quite easily. And we'll be seeing how that impacts the model. We'll be seeing how we can build those into a model based on your comments, okay? So I have an idea, a certain place where we can do that in just a few minutes, okay? Okay, any other questions? Was there another one over here too? Okay. Okay, ladies and gentlemen, so we saw discrete space. Let us now go to continuous space, but let's get our hands on the keyboard. Let's not be beholden to the models I provided you. Instead, let's build them up ourselves. Okay. So, ladies and gentlemen, I'd like you to fire up AnyLogic, and I'd like you to tell me, how do I create a new model? Remember, it's been a long night. Okay, file new model. Okay, good. We're off to a good start. Okay, new file, new model. Okay, file new model, and we're going to create a model that is going to be called learning mobility, and I'll call it SK. My tag of SK just lets me go find these models and post them to the site so I can share them with you afterwards. Okay, learning mobility SK. Okay, this is going to be a model that is purely designed to help teach the basics of mobility, because then we're going to apply those basics in a more sophisticated model. But I don't want it to get distracted from sort of the very basics. This model might even afford you a little bit of fun. Okay, so ladies and gentlemen, I'd like you to create a person class here. There's nothing that particularly distinguishes this as person. It's going to be entirely, so if anyone would like to call it something else, maybe we'll call it in deference to Vikram, we'll call it bat. Okay, let's name it a bat. Okay, let's go to bat. Okay, so we're going to call this a bat instead of a person, because we're going to be examining some behavior that's rather unhuman-like, inhuman. And it may be actually more indicative of bats. Okay. And ladies and gentlemen, I'd like you to go and let's lend it an appearance. And we'll do so with this pictures area. If only we had a bat.
How do you add other things to the picture file?
Okay, this is a good question. I know it's possible because my students unceremoniously added my picture to it one time, and I think this is before your time. But does any of my students know how do you add pictures to this? There is a way. Sorry? You can insert it? Okay. 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 And where's that located? Do you know? Yeah, I am kind of curious about that. Okay. Okay. Great. Great. I remember I used to do it with image. I didn't know if there's a better way now. Okay. Image. Yes. Yes. Here we go. Right. So we could add in an arbitrary image to our model. Okay. That's great. But for now, maybe what we'll do is we'll put in with deference to our bats, I think we'll put in a circle. So imagine a circular bat. Okay. And we're going to put that in to represent the bat. We can replace it later with something more textured. And some people might even want to draw a bat with a polyline. Okay. Okay, so folks, I would like now to, having lent this an appearance, although one that's most unbat-like, I'd like to go to main, and I'd now like to add a population of bats to our model. How do we do that? Okay, drag the bat onto the main canvas, and we'll call them bats. Okay. And this is going to be a population of agents, and it's going to be 100 agents by default. So you can just use it by the default, okay? And I'd like to lay them out in a random fashion, scattered throughout the model. We're going to have a static population. We're not going to be adding new ones, so we don't have to do it through the population itself. How do we have the model lay it out for us at random locations initially? Yeah, layout type random. We go to main, and we scroll down, and we go to layout type random. Okay? Okay, that's great. I'd like you to run this model and see what happens. Okay. Okay, we see a bunch of bats. Okay. 100 bats. That's great. Okay. So, ladies and gentlemen, the next step will seem a little bit confusing, but it's going to be our first step towards George's question, which is going to be adding custom visual interfaces to our model. Okay. Raheem, you might want to go over to that side in case there's any questions over there. Okay, we're going to go add, ladies and gentlemen, to main, we're going to go add a rectangle, a big rectangle that's going to delineate the area. Okay, so we're going to drag in a rectangle, and it's going to be from the upper place where these lines intersect, and it's going to go all the way down here to the right. But instead of trying to drag it, we're going to set its width and its height here in this user interface. The width to be 500 and the height, ladies and gentlemen, to be 500 here. Okay? So what did I just do? I just added this rectangle and set its width and height to be 500. I'm ignoring the Z height. Yeah, it won't affect our handling of this. It's a good question. Okay, ladies and gentlemen, the final thing I'd like you to do, which will be notable, I want to right-click on this, and I want to use order to send it to the back. This is visually, we want this little rectangle to occur behind the agent, so we can see the agents, the bat, circulating in front of this sort of canvas, or this rectangle. Okay. So now I'd like you to run this. Remember, it's really handy to run your model at many intermediate points to see if something's going wrong or if it seems to be working correctly. What should we see if we run this? Anyone? What do you think we'd see? Okay, there'll be bats in a rectangle, just like that. You notice one of them it's got its wing off the right-hand side because it's logically located within the bounds, but it's bigger than its box. Okay. So here we are. We can right-click on this. We could drag around. Fair enough. Okay. Does everyone see that? Who needs TA help? The TAs have been underused this morning, and they're ready to serve. Yeah. Yes.
So when we put that circle in the
Yeah.
center there, that's where it places them, right? So when it spills over, the center is still.
That's correct. Precisely. They're logically located at their center. And how do we know that? Well, if we go look at a bat here, we actually located this visually with its center at this crosshair, and that will mean that this little picture will be centered at their logical location. That's their logical location that occurs here. We could offset things, but then visually it's offset from their logical location.
Which kind of throws you off when you're looking.
Which would throw you off. This is why I always recommend that students, unless you have a really good reason, that you methodically center them so that you center things on that crosshair so that their logical location is the same as their visual location.
Would you ever put it at a different place relative, like if you put a house and you want the person to be standing next to the house?
Right.
Would you do something like that?
Yeah, you might do something like that. You just got to be careful and consistent in it. You don't want some agents to be offset and some not to be, and have lots of questions. Yes, Alan?
So that brings up something I've been curious about for a while. So you've got bat, right? And on bat, you've got the circle, but you could have other things. You could have text or whatever.
You could have a button for each bat.
Whatever. So
yeah.
Whenever you have the bat then as part of the population being shown in the environment,
yep.
It takes not only the circle, but all these other things too.
That's right.
What does it take? What does it leave and what does it take?
When you say take, you mean?
To represent the bat.
To represent the bat. It would use all the elements of the presentation. So if we started, let me see if I can address this quickly by saying, if you go over to bat, you notice there's these presentation properties here, okay? If I went and I wanted to add in, maybe I'll make it more bat-like by giving it some wings or something. I'll give it that. Maybe we should make them crinkly rings, right? So I'll do something like this, and something like that.
So anything from that text or anything from that presentation is going to show up.
So you notice that's under the presentation too. So this bat is asymmetric. Let me just move it back here. Okay, here we go. This is looking more. Yes. Yeah, I know. I didn't want to. Okay, so here we have them with those visual properties too. Okay. Okay, so maybe that's a little bit better. Yes, question?
In
Yeah. Yeah.
I know you said you want to put your agent on there before you populate your main.
No. So yeah, you want to put some visual representation, but you can change it later. It just. Yeah. You could put in the new image first and then delete it. I'd say. You might be able to do the reverse, but I'd say that's the safe way: is put in first and then delete the other one. Okay. So I mean, here we can show. I mean, folks, here to answer your question, I could delete this circle here, and now I should be able to run it now, and I should have my bats here, right? Yeah. Okay. So great question. Any other questions here? We're not doing anything too sophisticated, but you know, if someone in the room happened by chance to have any bat images, we could elaborate, you know, in a break and put some bats up there. Okay. Okay. So folks, I don't want to get too distracted by the batness here. So now what I'd like to do, folks, is we're going to give these folks mobility. We haven't done anything different except playing around with some presentation stuff. But now I'd like to put in place mobility, okay? I'd like to use mobility. The key thing with mobility, folks, is that AnyLogic supports moving in space, okay? So if we have agents and we need them to move, and this is all part of the slides that I've shared with you, here we have these things embedded in space, but we can move people around by calling move to. And this will actually initiate agent movement towards a certain location with a certain velocity. So we're going to be able to tell these agents basically move towards this, and they'll take care of flying in that direction. And moving along with a certain velocity, and they'll tell us when they've arrived. They'll tell us when they've gotten there, when they've reached their destination, and we can do things to them. We can alternatively jump to a certain location. We could set their rotation so they go at different angles, and we can query them. We can interrogate them as to their current X location, their current Y location, whether they're currently moving, where are they going, towards what, whither are they going? So towards what end? Through get target X, get target Y, and we can get their rotation. So ladies and gentlemen, let's use this. Enough of just discussing it. Let's use it. So, ladies and gentlemen, I'd like you now to go. Okay, I'm going to actually add back in this little thing here because it'll be easier for me to click on it. I could do it with a pure bat shape, but I'll do it with the circle. And I'm going to scroll down, and there's an advanced property here. Okay. Oh, I'm sorry. I'm actually doing the wrong thing. Sorry. I wanted to go to main. I wanted to click on the rectangle. Excuse me, folks. The click on the bats will come later. Click on the rectangle, and I want to go to advanced, and I want to go to this OnClick method. What that's doing is that's saying if you are to click on a place, then it can respond. So when you click on this rectangle, it can do something of significance. You notice in its AnyLogician sort of way, it gives you certain information. The X location and the Y location of where you've clicked. Okay? So it's going to give you the sort of information to use in your handling of that click. Okay? So what I'd like you to do is I'd like you to hear, we're going to go through the population, and we're going to, for each of them, we're going to get them to move to the location where we've told them where we've clicked. So, ladies and gentlemen, you've seen it yesterday in your first time going through the entire population. Do you remember how I did that? Remember in one of the examples yesterday, I went through each person in the population. I added their information into a histogram. Do you remember what construct I used? What type of so-called statement did I use? Okay, it was adding data in, and what sort of statement was it? It was okay, I'll tell you a story. This is a true story. So I've been involved with computers for a long time, and probably before many of you were born. So I first started getting really interested when I was around 10 years old or something like that. And I was sent off to summer camp, and I spent a lot of the camp programming a little TI calculator in assembly language. You could program it to perform, like to shoot a cannonball and have it land somewhere, little simulations, right? So anyway, I was really, really interested, but all I could have is this little calculator. And then I heard that our high school, later that summer, was going to offer a class a little class in Introduction to Computers. So I got all excited. And, you know, I was like 10 years old, and I went to the class, and it was in this high school. I was just overwhelmed, these big walls, big doors. I remember walking through it and seeing people doing welding. Oh, what sort of place is this? But I went and I found this lab, and they had these computers there. They had these computers lined up. These are what are called, Kurt wouldn't probably know anything about this, but it was these things called teletype machines, and they would spit out this paper, you know, it would spit out, sometimes quite high rates, and, you know, really thick sort of sheets of paper, I mean, really wide sheets of paper spitting out. And then they also had these teletype machines that were basically these things that look like TVs, cathode ray tubes with these nice keyboards in front. For anyone who is interested, it's an older sort. It's a PDP 1134, I think they had. In any case, it was a digital machine. So I was there, and I was just in my element. It was just like a dream. I could go and I could do things on these machines. And so time passed quickly, and this class was going on, and honestly, I wasn't paying much attention to the class. My attention was entirely on the computers. And then the professor announced, it wasn't a professor, he was a teacher. And and all the other people were like, they seemed like 40 years older than me. Some of them I think were close to retirement. Some of them were really, really old, like in their 30s, and they were tall, and I didn't have anything to do with them. I just had things to do with the computers. That was the point of my focus. Okay, so it was great. I was in my element. I got to use the machine that spat out the paper. I got to use the machine that allowed me to use the TV-like thing, and it was great. And then the teacher said, "We're going to have an exam." I don't know what an exam is. It sounds bad though. So we said, we're going to have an exam. It's going to be a final exam for this course. And I thought, oh, man, I don't know what's going to happen because I haven't been listening to the course. I've been listening to is the computer. But he said there's going to be a review session. So I thought, this is going to be great. I'm going to get to go to this review session and learn the material. So his review session, he was saying these various things, and I was trying to listen to them and so on. But he was also, what really scared me is he was asking people questions as part of the review session. He was asking the people in the class questions. And so he was walking up and down the halls in a most unsettling sort of way, between the chairs, asking questions. And just as would you know it, he was walking down the hall, he said, suppose we had a situation where we wanted a computer to go every number from 1 to 100 and do something for each of those numbers, maybe print something out. How would we do that? I didn't know what to say. And he came up and he stopped and he came and stopped in front of me and looked at me. He said, so how would we do that? I looked at him and I said, I don't know. And he said, I'll give you a hint. That is an L, 2 O's, and a P. Okay? And I looked at him and I said, pool? It is absolutely true. It is absolutely true. I think he gave up on me. I don't remember taking the exam All I remember is those computers. Look where I've ended up. So, to recap, suppose we wanted to go through each person in the population and do something for each person. What would we use? I'll give you a hint. It has a L, two O's, and a P, but actually in more specific terms it has an F, an O, and an R. And it's not a ROS, okay? So what is it? It's a what loop? It's a for loop. Okay, good. Good. That almost was a Greek chorus. Okay, so remember this? We said for person P in, oh, it's not person, is it? It's what? It's a bat for each bat B in bats. Okay? For each bat B, we're going to move that bat towards where we clicked. And where did we click? How do we know? Well, if you look at this light bulb, it tells us where we click. Click X, click Y, the coordinates of the click. So we're going to say move the bat. We call it B. Maybe we want to call it bat to be consistent, you know, so we know it's a bat. We're going to move the bat dot move to click X, click Y, and then we're going to have a semicolon there. Okay? There we go. Okay? So what this is saying is we're going to go through each bat in the population called bats. So for each bat in turn, we're going to call it bat. Call it bat. First bat, we're going to call it bat. Second bat, we're going to call it bat. And we're going to tell that bat, you tell each bat in turn to move to the certain location where we've clicked. Does that make sense? So we're clicking on this place, and we're going to tell all the bats converge on this place. Is that reasonable? Well, or is it at least understandable? Okay. Yeah, no, I'm not asking whether it's empirically accurate. Okay, so ladies and gentlemen, I'm running it. Who needs TA help? The TA stand ready. You know, it took me years to get that loop right from Pool. And you know, I understand you may need TA help. Okay, ready? Should we click, folks? Do you see something moving? Do you see them? Okay. Okay. Okay, so they're all bunching up there. There we go. And now it almost looks like one bat. Why is that? They're all overlapped. Okay, ladies and gentlemen, so we've exhibited some aspects of movement, but we're going to do something a little bit more textured than this. We're going to get these bats to move in a more entropic fashion. Okay? Okay, so ladies and gentlemen, we're going to give these bats behavior. What's one way we've encoded behavior before? Using a what? A state chart. A state chart. So we're going to go to bat, quite literally, and let's go to the bat. Ladies and gentlemen, open up your bat, and ladies and gentlemen, we're going to add a state chart. How do we add a state chart? Okay, good. So where do we go for our state chart? Palette. Okay. Okay. And we're going to call it mobility state chart. Mobility state chart. Okay. Who needs TA help? The TA stand ready. Okay. This is going to be called mobility state chart. Okay. And we're going to add a single state in this state chart. This will open up some eyes as to sort of how you could use state charts. The single state is going to be called moving with a capital M. Okay? Okay, now we're going to have one transition from this state back to itself. So I drag the transition over here, and I'm going to click in its middle, and I'm going to place it down here, just like that. Okay? And this transition is going to be called the resume moving transition. And it is going to be an agent arrival transition, which is one we haven't used before. Okay? And ladies and gentlemen, so we just added this state chart entry point. We added this state, and we added this transition. I dragged it in, I clicked in its middle, and I bent it over to go back to the state. So when we stop moving, we're going to then pick a new location and resume moving, basically. Okay? So it's going to get us back moving again. And it's an agent arrival transition, hence that little flag. It's an agent arrival transition. Okay? People comfortable with that? Okay, now we have to put in one key piece of logic, and then we're actually basically done with the core logic of this model. Yes, Dylan.
Can we slow down for a minute? I see that people are not quite caught up with the state chart thing yet because of other errors that have happened along the way.
Okay, sure.
45 seconds of recovery.
Okay, yeah. Chris.
Can I take 20 of that?
Sure, sure.
So I just want to contrast the return transition that you put up there with the other version, the one we did a couple of days ago, where it was just within the state.
Yes.
Right.
Yeah.
Where this one actually comes out and then goes back.
Right.
Are those distinct anywhere, or is that just visually more aesthetically pleasing?
So you asked me an uncomfortable question, and if you had asked me 3 months ago, I would have said they're definitely distinct in this sort of way. There was, and let me tell you the ways that it was my understanding that they were distinct, but an experiment recently made me question maybe that changed for AnyLogic 7. So I thought they were distinct. I thought this one where it stays within the state, it actually doesn't end up recomputing the rates of outgoing transitions and so on. And I thought you had to come out and go back in to do that. But there was an experiment I did in North Carolina which seemed to contradict that. But then I did an experiment yesterday which seemed to suggest that it was still true. So I will get you a definitive answer on this. But I believe that in this case it doesn't matter. The only question is, when do they differ in terms of recalculating rates coming out of the model? That's the essential issue. Yeah, otherwise they will, I think, still execute the entry action. Yes? Oh, the question was, is there a difference between a transition that comes out and goes back in versus one that stays inside? Both are self-transitions. And my understanding was that there was a difference in as much as with the one coming back in, it recalculates the rates associated with all outgoing arrows, outgoing transitions. But I need to double check that because something I saw in North Carolina made me think that maybe now they've removed that difference in AnyLogic 7. Yes, question?
Sorry, I think old not obvious, but it wouldn't calculate, it wouldn't perform an exit action.
Okay, you mean internally? Yeah. Okay. That may be in the entry action as well. Yeah. Yeah. So the question there is, would it perform the entry and exit action for this state if it just stayed internally? And I agree that should be double checked, but it may be you have to come out and in again to do that. And we're going to be using the entry action, so it's important in this case to come out and in. Okay. Thanks, Jeff. So I think we need to do some verification because I thought I saw in AnyLogic 7 pretty clear evidence in North Carolina that distinction between the two types of transitions was removed, which would be interesting. In any case. Okay, so folks, the final thing we're going to do is in the entry action, we're going to actually get, so this bat is moving. This bat is going to move, and once it's reached its destination, it's going to pick another point nearby to move to. So it'll sort of flutter, okay? And what we're going to do, ladies and gentlemen, is to take our current location and move to something that's offset from it by a certain amount, okay? So this is how I'm going to express it. This dot move to, this is how I move to a certain location. We're going to give it an X and Y location to go to. Ladies and gentlemen, for the X location here, we're going to give this, and I hope I don't give poor Jushin a heart attack here, because as I told the group, Jushin, to draw from a normal distribution, you first specify the standard deviation and then the mean. It's in the opposite order that I think most people would expect. So normal 20, comma, this dot get X. Can anyone interpret that for me? What is this doing? We've seen all the elements of this yesterday, but what is this actually computing?
Getting the position of the current x-axis and then varying somewhere in the normal distribution.
Yeah, that's right. So, very good. So we're going to draw a value, we're going to sample a value from a normal distribution with a standard deviation of 20 and a mean given by our current location. In other words, if we're currently at this certain location, our X and Y location is maybe, 20, comma, 31. Maybe now we'll pick a value whose X location will be down here at, 16.31. And we're going to do similar things with the Y location. We're going to perturb that by the same basic amount. So we'll end up with one that's here being here. And we're going to then move towards that place. So tell me, ladies and gentlemen, that's the X location. What should I fill in for Y? That's right. So it's the same basic thing, but replace get X with get Y here. Okay? So that's what we want. This is exactly what we want. And I'll put this up on the big screen. There we go. Okay? Okay? People comfortable with that?
Could you narrate in English what it means again?
Sure. So we're currently at a position that's given by, so we're at some position, right? Maybe we're at 20, our X location is maybe 20, our Y location is 31. So if we call this dot get X right now for our current position, what is it going to return? If we're at 20, 31, what is this dot X get X going to return? 20. If we call this dot get Y, what will it return? It will return 31. Good. That's current coordinates, okay? It will return 31. Good. Okay, so those are our current locations. This is our current location, say it's 20. We're going to draw a value from a normal distribution that's centered at that location. So in terms of the X values, it's going to look something like this. That's horribly biased. It's going to look something like this. Okay. Oh gosh. This is most unsuitable. Okay. Well. Sorry. This is horrible. This is why I need a computer, folks. Okay. Yeah. So here we have a normal distribution in X centered at 20, and we're drawing a value from that normal distribution. We'll sample one. It's much more likely to be in this region than it is to be way out here. We're going to sample one from there, and we're going to get a value of 16 from it. And then we're going to do a similar thing in the Y direction and sample from a normal distribution and get a value out for that. So we're going to get a value out centered on our Y location. So our Y location is 31. We're going to have a normal distribution centered at 31, but have a standard deviation 20. We're going to pick a value for that, and that's going to give us perhaps a value up here. So we're going to have another one here it's kind of going to go like that. It's coming up, and that's, we're going to pick one for the Y location. So then we're going to say move to those locations. This is our X, this is the resulting X, and this is the resulting Y. Does that make sense? Okay. Okay, sure. Other questions about that? Dylan?
I guess I'll just point out to anybody who's looking at this and is less familiar with statistics, that statement up there effectively says, take where I currently am, and take roughly 20 paces and then up to 20 paces in any direction. So like, I'm right here, plus minus 20 in this way. That's the next target. With the normal distribution thing, it just means that you're more likely to go closer than you are to go further away. The non-statistic people here like me, that's the dumb explanation.
Yeah. 68% of the time, I think it's going to lie within that band of plus 20 to minus 20, if that's not mistaken. Yeah, around your current position. Okay. 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 Are people comfortable with that? Should we run it? Should we run it? What do you think? Okay. Okay. And so let's run this thing now. Okay. Okay. What do you see? Okay. Okay. They're moving around. Okay. You can zoom out by holding down Control and mouse out, and you'll see that they're kind of moving around in a quite entropic fashion. Now you can click, and oh, look at that! You see that, folks? So click on the rectangle, and then they'll converge. Why are they converging like that? Well, we're telling them to move to that location, and they pick that as their target. Okay? So this is an exhibition of mobility here. So that's right. So they all collapse together, and then they start diffusing because they've reached their destination, and so they'll start diffusing again. This is probably not too similar to actual bat behavior, but it does teach them basics of movement. Yes.
Having your wings on there reveals something that I hadn't noticed before, which is, well, they actually orient in a direction.
They reorient. They actually rotate themselves to go in the direction that they're headed.
Can you give me an illustration of how that property is?
Yeah.
I want to call it facing, marching direction, whatever.
Well, it's just.
That it does that.
Yeah, it's just. Suppose you had a. Okay, this is gonna be horrible. Suppose you had a car, like this, right? It looks like a boot more, but suppose you had a car here, and you had a model with cars, and you want them to go in different directions. You might plausibly want them to kind of point towards that direction.
But it's just an aesthetic thing.
It's just an aesthetic thing.
There's nothing functional.
No, but you can tell it to not do it, too. You could tell it to set the rotation, yes.
How do you keep the movement constrained on the box?
Okay. Would you like to do that? It wouldn't be hard to do.
Keep them in the square.
Okay, do you want to keep them in the square? We can keep them in the square. The bats in a box? Yep. Okay. So let's keep them in the square. How can we keep them in the square? Let's think about it. Ladies and gentlemen, how can we keep them in a square? There's a hard way, there's an easy way. The hard way is to every so often peek, am I in the square, or am I getting close to the edge of the square, and reorient yourself. The easy way is to just never send them outside the square. In other words, to only send them somewhere else inside the square. And there's ways to do that that are more statistically advised, I think, and ways that are not so statistically advised. The really trivial way to do it, way that's that's very straightforward would be to bound the value returned by normal. So it always lies, you clip it. You clip it to be within the bounding box. So I don't know if you folks want to do this, but we could take the minimum of this value and 500, and then we could take the maximum of this value and so I'll actually rework this. I could take the minimum of 500 in this value. So if it's bigger than 500, it's 500. If it's less than 0, it's 0. I could do something like that. So now let me count my parentheses here. 3, 4. Okay, so I need a fourth over here, I think. So I could do something like this, and similarly for this. Now this is a quite horrendous thing to do. I would use a function if I had my druthers, but this would actually bound them to be within the box. The problem is it's going to lead to artifacts, because there's a bunch of times where you would have picked outside the box, you're instead going to tell them to go right at the edge of the box. And so it would be better to resample. It would be better to, if it's outside the box, to draw it again and again and again. But this will work. It's painful to look at, folks. And I would create a function that would do this in little pieces. In fact, I'd create two functions. One to have a sort of nominated one, and then that would hopefully resample it. But if not, at least it would bound it. But this will work, I think. You want to see the bats in a box? Oh, okay. You want to. Okay, you actually want to put that in place? Okay. Here we go. I'll put it up on the big screen. There you go. Okay. Okay, so what am I doing here? What in the world does that mean? Well, what in the world that means is that we're going to draw a value from a normal distribution, centered at our current location, having standard deviation 20. So that's going to be a perturbation of our standard location, the x direction. But we're going to take the minimum of 500 in it. So if it's bigger than 500, we're going to use 500. If it's less than 500, we'll use whatever was returned here. And now, considering that, we're going to take the maximum of 0 and that thing. So in other words, if this thing is greater than 0, we'll use it. This thing is greater than 0, we'll use it. Otherwise, we'll use 0. If this thing is less than 0, we're not going to want to use it. We're going to use 0. There we bounded them to that box. Does that make sense? That's not a particularly good way to do it, because it leads to artifacts at the edge. It leads to sort of weird things happening right at the edge. Okay? Okay. Okay, ladies and gentlemen. So are people comfortable with that? Okay, sure. The really, I don't like doing this at one place. It's just I haven't introduced functions yet, and so it's not so easy to do it. Yeah, I knew that they allow bounding thing, but I don't know if we want to explain the shift and double. Yeah. Thanks, Mitchell. Okay. So again, this is the most unpleasant way to do it. Until I introduce functions, this is kind of we'll have to stomach it. But the basic deal here is if it's greater than 500, we're going to use 500. If it's less than 0, we're going to use 0. If it's somewhere in between, we'll use that number for x and for y. If x is greater than 500, we'll use 500. If it's outside the box, we'll use the edge of the box. that edge of the box. If it's to the right of the box, we use the right edge of the box to go to. If it's left of the box, we'll use the left side of the box to go to. If it's above the box, we'll use the top of the box. If it's below the box, we'll use the bottom of the box.
And interestingly, or maybe when you run it,
yes,
it's staying in the box, but the behavior is quite different.
Yes, I think it's because of the artifact. Do you want me to keep this up here on the screen longer? Yeah? Okay.
They keep doing that. If you watch them when they come, they're not scared off anyway. They're scared of that.
I'm wondering, that looks to me, you know what that smells to me? That's a diagonal. That smells to me like you've missed one X and Y.
Yeah,
so I think you must have get X or get Y repeated twice, and I bet it's a get X. There you go. There you go. Yeah. One recognizes the scat of defects after a certain time. It's sort of just like someone like Trent can immediately recognize bighorn scat. I can recognize the scat of a repeated thing. Yeah. Yeah. It has the same smell. Yes. Yep. Yeah. Okay. Yes. Okay, great. Let's finish with that, and then we'll go on to a separate example. And this will link in with George's question. We're going to use George's question to prompt this, okay? So, ladies and gentlemen, so there's a question about how could we set their speed, okay? So let's run it with this, and by default, now we could speed it up visually like this, and here we'll note that they are staying in the box, right? Okay, but if we want to speed it up by default, so we could change their speed, we can do it in one of several ways, but let's try this. Let's go to main, and we're going to drag into main from the control palette. We're going to drag in a slider, okay? We're going to drag in a slider here, okay? And this will be called velocity slider, okay? We're going to set it to a minimum value of 0 and a maximum value of 50, okay? The default value will be 10, okay? And you'll notice there's an action thing here. This is going to allow us to say, what do we do if this slider is changed? What do we change? So we're going to have to change the velocity of each and every bat in that population. Is what we're going to have to do. Okay. Oh, sorry, I meant to say 10, not 110. Thank you. 10. Sorry. So for the action. So ladies and gentlemen, suppose I wanted to go through each person in a population, each bat in a population. And for that bat, I wanted to do something to that bat. I want to go through each in the population and call it bat. How would I do that? A for loop. Okay? For each bat, and how do what's the magic character I put next? Colon in the bats. For each bat in bat, what do I want to do? I want to set that bat's velocity. Bat dot set velocity. I want to set it to a velocity. Where am I going to get the velocity to set it for it? I'm going to get it from the slider. Oh, sure. Like that. Dot, and I can call get value. Okay, there we go. Ladies and gentlemen, I'll put it up on the big screen. Okay, there we go. For each bat and bat, set the velocity of that bat according to the slider value. So this slider is a certain value. And when it changes, it's going to wake up and say the value has been changed, and it's going to run this code. It's going to go through each bat in the population and set its velocity to whatever the slider value holds. Is that okay? Is that okay? Okay. Great. Great, great, great. Okay. What's that? Do people want this up on the thing here? Remember, autocomplete is your friend. Remember, you can type here velocity slider like that, right? Especially when you make sure that Jushin knows about the autocomplete control space. Yeah. People want this up on the board more? Want it up there? Are people done? Do you want to run it?
You go to the extremes, the whole thing crashes.
Is that right?
Yeah, you go right 0 or right at the top, the whole thing crashes.
Oh, that's interesting. Okay. Oh, gosh. Gosh. What the heck?
Yeah, good. Yeah, you get very unhappy at the extreme.
Okay, that's, wait a minute. There's something. Wait a minute. Okay. Okay, that's most unhealthy. TAs, I need your help. Yes.
I think I've had problems with this before. It's like you have to pause the simulation or something, trying to make multiple changes or finishing doing it.
Okay, sorry. Did I say, it shouldn't be get value. Oh, okay. So get int value. Okay, that's interesting. Okay, let's try that again. Okay. Okay, but it's not clear to me.
No, you still get it. You still get it.
You got another number value when you went down to 0.
Yeah, no, it's not. It's actually
It's like it's calculating how quick is it arrive.
Precisely at the destination. Right, but it shouldn't be able to calculate that. Okay, folks, we're gonna have a health break. Okay. Okay. What is going on here? Yeah.
Put that into a separate variable, and then when the maps decide to go to new locations, then they take value from that variable.
Okay.
What somebody was saying is that it might actually impact the calculation, how long it will take them to get to a location, which might screw up the calculation.
State chart. Okay, that will work. Yeah, I believe Dylan is absolutely right. That should work. So we could get it to set a variable, or actually, well, Dylan's stomach would turn, and so would mine. But this thing could actually just directly set velocity from the value of the slider.
What about
So you could do this dot main dot set velocity based on slider or velocity slider. Sorry. Velocity main dot. Yes. Oh, sorry. Sorry.
Yeah, what you're doing
what am I doing?
work as well.
Yeah. So this dot main dot velocity slider. Yeah. There we go. Oh, sorry. The velocity slider dot get value.
Get in value.
Why get in value?
Is it? Oh,
No, get value. It should be fine. It should be fine. Yeah. Get in value is just if you want it as an integer, I think.
And then I think we got to change names so you get rid of the code in the
And it's still it.
Oh, yeah, because there's still code in the slider, right. Okay, yeah. Okay, there we go. Yes.
Does that bug only happen when you get to 0?
I think that bug happens
No.
because you're changing the velocity of them without
They're arriving?
Yeah, which might have some sort of bug which might like impact the negative.
Yes.
If you put in a state chart,
Yeah.
for each,
Sorry?
put in a state chart. In Paradigm in the person or? So the fix for that.
Put in a state chart?
You don't need to put the for loop to it, just put the velocity, call it from main.
Yeah, there's no loop now.
Oh, there's
No loop now. Yeah, with this.
Did you put in a state chart or where?
Yeah, it was changed in the state chart to set the velocity. Yeah, but
Is that working? Working now?
no, because a bunch of them are frozen.
Why?
Because they never reached the location.
Okay, yeah, got it.
Yeah. Hey, Dylan.
Because of rate?
Sorry, just wanted to warn you. There is a bad side effect of that fix. Watch this. If you drag this down to 0, they'll never move again.
I can still remember calling like these stuff.
The bugs in the state, like the transition from the state chart,
Yeah.
when it tries, it doesn't know how to deal with it being a 0 because there's a division.
Well, the issue is more. I mean, the reason it freezes is because you basically set their velocity to be 0, then they never arrive, and therefore, because they never arrive, they're not going to ever be reset as to what they're, to where to go next and to set their velocity.
Would there be potential bugs in AnyLogic?
No, it's just a logical thing. If you set their velocity to 0, they'll never arrive.
But if you do have an arrive by check, people might not catch that bug if they're not computer scientists, right?
Yeah.
Would it be useful to write that down and send it to them?
Yeah, I would like to write down this issue. I mean, it's evidently a problem that you can't dynamically set the velocity in motion, which I don't understand.
You just move the velocity change so that after you've got the move, so it makes the move with that velocity, and update the velocity after that. That way it would have to finish the move.
Right. Well, okay. So the move is asynchronous, so it calls off to it, and it's going on. It goes on immediately to the next thing to do while the move is still continuing.
I just put in your state chart.
Yeah.
The move command, but you've done the velocity
before it. Yeah.
I sure assume that in Java it's going to do one statement, then it's going to do the.
Yeah, which is okay, but if you put it right after, it would just start the movement, but it goes on in a separate, as we say, thread, so it would just go on and execute this immediately as well.
Put like a wait then on the depending on the make sure the move's done then.
Well, I think the thing is the move is done at the beginning of this time. The last move is done at the time that it comes in here, because they do on arrived after they're done with their last move.
Okay. Well, can that then be put into the transition for the arrival transition?
Yeah, you could do that, but I don't know that that's gonna address the issue here. This new issue is that, fundamentally, and I think this is just a logical thing, their velocity is only reset once they've arrived, right? And so if they're going at 0 velocity, they're never going to arrive, and therefore they're never going to restart movement because they're never going to get the chance to reset their velocity, which kind of makes sense. If they're going at 0 rate, they're never going to arrive. They're never 0 velocity. What doesn't make sense to me is why you can't set the velocity dynamically while they're moving. I mean, they should be able to recalculate.
I should have just been to do the way the formulas are calculated and that.
Yeah, but they should be able to redo that, I would think. You know, it seems to me kind of strange that...
Probably that as it's making the change, it's set temporarily to 0, and then it's going to get when it's trying to calculate the arrival time, which is that state dynamically, it's probably giving not a number because it's dividing through by 0. So you may be able to get away with it if you just set it to some really, really, really small but not 0 number. But that's probably not a...
Well, yeah, I mean, it was causing these problems for any velocity. I mean, any altered velocity. That's the weird thing, you know. In other words, it was causing it up here for with this thing here. It was causing it, you know, for any setting it to any alternative velocity. So set velocity, you know, just as a sanity check, I'm going to set the velocity to 20. Just ignore the value. I want to be sure that it's getting sane values towards them. Okay, here we go. I'm going to change this. Yeah, you see, it's just setting it to any value gives us problems, and it's.
I've had trouble with something similar where I had like a resource and I was trying to change the resource. It just doesn't like change it as the simulation is running. I had to essentially pause it every time. Because it was like somehow there's like a lag between how quickly it calculates it out.
Yeah. Well, here it's obviously having the trouble in the call to move to. So the next one that's sort of going to move, it's for some reason had this trouble.
But I noticed that can you copy all these errors and then send them to me? I'll write them down in the bug.
So I noticed it's not on the first bat, it's on like some random number of bats. So it's like
yeah, it's on the next bat to move, I think. I think it's on the next bat to move, but okay.
I shared the bug report with you on Google Drive.
Okay.
AnyLogic bug is what it's called.
Okay. Oh yeah, I got that. Thanks. Okay, great. Yeah, I'm not sure why that should cause a problem in the next move. So it's entering the state, it's then doing a move to. Why should that cause any sort of problem? It's almost like its new velocity is unknown. Let's do this. Let's get it here to print out here what its velocity is. So trace ln, my velocity is get velocity, okay? And let's run this. Great. Okay, so, okay, and now I'm going to try going up here and, okay, and hey, come on.
it's like having
Okay, let's slow this thing down. Okay, okay, my velocity, yeah.
Is it because the print state is giving you enough time between?
That's what I'm wondering. I mean, it may not have caught up yet.
One of those things like
yeah,
you'd like to have a pause, like
precisely.
doing things simultaneously, so you can just put like a little small pause into it or pause the simulation.
That's what I'm suspicious of now. Oh, wait a minute. Sanity check. There's another reason. I mean, it's still mysterious, but first of all, we set this to be 20, so we should do, you know, a velocity slider dot get velocity. That's what we should do. Okay, and get velocity. Oh, get value. Gosh. Okay. Okay. Yeah. Okay. There we go. Watch this. My velocity is 15. It's the first one for which the velocity is 15 that it's saying this. And I don't understand why that would cause a problem at all.
To adjust their velocity in real time?
Yeah, and especially because it's, yeah, oh, actually, I think I got it. I don't like what my theory is, but if my theory may be, I wish it weren't so, but it may well be. I've just got a suspicion. Maybe it has something to do with that it need to have known it. Okay, let's just try this. I hope this is not it, but that dot on change.
What's on change?
It's basically notifying it of the change, saying, hey, wake up and sort of recompute your stuff, okay? Nope, nice theory.
I just did a workaround where I, like,
okay.
when it gets to its position,
Yeah,
or when you
well,
put it somewhere new.
that's what we did. The problem with that one is if you set it to 0 velocity, then they never get to their position.
Right. Or if it's even just really slow, it takes forever to get there.
Exactly.
I just worked around that by putting also recomputing the velocity when you click on the new location.
Yeah.
But still isn't not ideal.
No, we need to get to the bottom of this, and I think I'll get one of the TAs to work on it, because it doesn't make a lot of sense that you can't change the velocity and then set them moving in another direction. Why can't you change the velocity while they're in motion? I've never seen this before in AnyLogic 6, and I did things like this, where I changed velocity while it was moving. So it is possible to bug. Yeah. So probably, watch this. I don't like doing this, but let's just try it this way. This I think will work as a workaround perfectly fine. This is ugly as sin, but let's just do it. Get her done. Okay. Here we go. Okay. Timeout. Every timeout 1, we're going to set the velocity. Yeah, according to that thing. So I don't like it, but let's give it a try. This dot set velocity. This dot main dot velocity slider velocity. Hey, velocity slider.
It's a problem where sometimes it doesn't know what to do.
Indeed. Get value. Yeah, here we go. Okay, boom. Oh, okay. What's this dot main dot velocity slider dot get value? Okay. No, it should be fine for that. Cannot return a void result. Okay. Oh, of course. What am I doing? This is a timeout. This is the action I want. Yes, it didn't know what to make of that because I was giving a statement or an expression is required. Yes, of course. Okay, there we go. Okay, now I suspect it will work okay, but
yeah. So that's kind of like some sort of sequential.
Well, it's just periodically telling it, hey, set your velocity from this thing. Ugly as sin. I don't like it. I think it's probably a bug in their implementation. I'm going to complain about it. But that is a fix that works.
Because they're just basically trying to force it to do one calculation, then do the next, not trying to do it simultaneously.
Well, it's actually recalculating when it's going to arrive. That's the deal. It's forcing it to recalculate when it's going to arrive. I think the problem is that associated with that, I think it figures out when it's going to arrive based on its current velocity. And then if it actually arrives, when it arrives there, it freaks out because it says my velocity is not consistent with the time that I arrive, my current velocity. And so what this is doing is it's getting it to recalculate when it's going to arrive periodically based on its. In fact, I don't even think we don't even need this thing here. We could do it this way, but we don't even need this. Or do we?
It's just weird because the fact that it's saying it's not a number, it looks like it's divided by like zero or something like that.
Right, I know.
Which is very strange.
Which is very strange, and I think it's a bug.
Because it means it looks like it's trying to recalculate the
That's right,
arrival
precisely.
time, but it's not doing it right.
It's not doing it right. Yeah, exactly. So, okay, I think we're going to cut our losses, and I'm going to report that as a bug, and we'll get people in here. Okay, folks. So we're gonna resume here. We're gonna resume. Okay. Great. We're going to use our closing time this morning, however, to further reinforce a more realistic movement, or at least a more health-oriented movement model, which also is going to get into hybrid modeling. And I picked this example, and I worked late into the night last night, maybe a bit too late, to pick out an example which would address the needs of multiple groups here. This example, ladies and gentlemen, is for you, okay? And we're going to go our way through it. And forgive me if I sometimes play a bit out of tune.